Hello everyone, and welcome back to the pilot module for Purdue University's MBSc Professional Development Program. In this video, we will explore the concept of systems in depth and utilize case studies videos which we watched in the previous section to discuss these concepts on Brightspace discussion boards. Once we develop an understanding of systems, we will then proceed to the next section of systems thinking in another video. So one of the first steps in systems engineering is to realize system and its attributes. Model-based systems engineering allows for model-based representation of a system and its attributes and links them for more holistic study of systems. In this video, we will learn about definition of a system and look at different types of systems with a focus on engineering system. We will then explore the attributes of an engineering system that will help us distinguish the system from its surroundings and develop a holistic understanding of its parts and their interactions. So what is a system? I imagine many of you must have heard this famous phrase before, that the whole is greater than the sum of its parts. In the simplest of terms, this whole is these systems. What this implies is that a system is composed of parts, and together the sum of the parts provides a capability which can only be attributed to the whole. If you recall, in the previous video, we looked at many examples of a system from an aircraft to a manufacturing process. Considering aircraft as a system, one can identify its parts and see how the whole, that is the aircraft capability, which is greater than the sum of its parts, emerges. An engine cannot fly on its own, and a wing will not produce lift without moving through the air. Together, the engine and the wing, along with other components, help the aircraft fly. So here are some formal definitions of systems which reflect a similar theme. A system is an assemblage or combination of things or parts forming a complex or unitary whole. A system is a set of interrelated components working together towards some common objective. A system is an arrangement of parts or elements that together exhibit behavior or meaning that the individual constituents do not. So as we step through these definitions, we can quickly observe some commonalities among these definitions. A system contains multiple components. These components are connected to one another, and together they achieve a purpose. Now, this definition can be applicable to a variety of phenomena in the world around us. A system can be simple or complex. A simple system is where there are relatively smaller number of parts and interactions are easily understood. For example, let us take a look at the mechanical pencil. It has a lead, right? It has a lead, it has an eraser, a spring mechanism, and a body, and we can easily understand the function and interactions of these parts. On the contrary, a complex system is where there are a large number of parts and multiple interdependencies between those parts. For example, an automobile with 30,000 parts can be considered a relatively complex system as compared to the pencil. So I say relatively as there is still some contention on when a system becomes a complex, as we will see in the examples on the upcoming slides. However, before we proceed, I'd like to emphasize that a system based on the commonalities among the definition is not limited to a product, for example, a pencil or an automobile. It can be a process, a service, or even an organization. A system can be natural, socio-technical, or technical. Now, systems engineering, and in particular systems thinking, which we will cover in the next video, can be applied to all these types of systems. Now let us look at examples of some of relatively complex systems. Compared to a pencil or an automobile, one would consider an aircraft a fairly complex system which has many technologically sophisticated parts and many interdependencies. Here is another example of manufacturing production system for a film cap with different components and parts that work together to achieve a common purpose, which cannot be achieved by these individual parts alone. How about some other systems, like a healthcare system, which is shown on this slides, or the defense acquisition system shown here on this slides? The definition of system still applies here, and their complexity is rather unquestionable. How about we have a quiz on these slides, where I would ask to list different components of these systems and draw their connections. Just kidding, we'll leave that exercise for our graduate students. So most of these examples represent an engineered systems which are specifically designed to achieve one or more than one intended purposes. These systems have an anticipated operational environment, are subject to physical laws and regulatory constraints. A different type of systems are natural systems, which, as the name implies, exist in nature and are not under the direct human control. For example, a hurricane, as shown on this slide, or a planetary system. However, the definition of system can still be applied to these natural systems via human thought process. In this program, we'll focus on the technical and engineered systems. So let us take a look at some of the attributes which will help us study these systems. So there are 8 attributes that we will discuss in this video, and their understanding will eventually help us develop models for systems. These attributes are purpose, function, structure, behavior, boundary, environment, interface, and hierarchy. These 8 attributes can be directly related to a system and the definition of an engineered systems. Let's investigate these concepts further. For an engineered system, there has to be a purpose, as an engineered system is made to achieve one or more objectives. This purpose identifies what the system does, that is, what function it performs, what is that capability which becomes greater than the sum of its parts. Now, since there are parts, there must be a structure on where these parts are located, how are they connected and enclosed. Finally, there is system behavior, is how the interactions of these parts enables the system function. The idea for model-based systems engineering is to represent these attributes of an engineered system in the form of digital models, which can then be shared across multidisciplinary teams. Remember, we have talked about that MBSE is a transition from document-based systems engineering to model-based systems engineering. These attributes are some examples of artifacts which are created as digital models in MBSE as opposed to being described in lengthy documents. Since engineered systems have an anticipated operational environment, there must be a distinction on what is part of the system and what is in the environment. The system boundary forms this distinction. The elements and parts within a system boundary remain under the control and ownership of systems engineers. The systems engineers and the multidisciplinary teams remain in charge of defining how the parts interact with one another within the system's boundary by defining interfaces between the parts. These are called internal interfaces. Outside the system boundary is the environment in which the systems operate. Since we typically don't make systems to be deployed in a cave in total isolation and forget about it, a system contributes to and consumes from other systems in its environments. The interface of the system within its environment are called the external interfaces. And in order to develop a model of a system, the relationships between the parts inside the system and between parts inside and outside the system and the boundary and internal and external interfaces must be shown. Another important attribute of a system is a system hierarchy, which helps establish a system of interest. As we look inside a system, we can see that there can be technologically sophisticated parts within a system that in their own regard can be classified as a system. These components are often referred to as subsystems and have their own attributes such as subsystem boundary, interfaces, purposes, functions. For example, when looking at an aircraft as a system of interest, one could see that the aircraft engine is a subsystem, but for the engine manufacturers, the engine is the system whose external environment is an aircraft. It is often said that one person's subsystem is another person's systems. It is the system hierarchy and the system boundary which set the context of what is the system of interest. For a given product or system, the systems engineers and project managers need to understand this hierarchy to see how to integrate the various components together in a purposeful way, while domain engineers who build the parts and components needs to see how their pieces contribute to the top-level systems. With model-based systems engineering, we can use models to assist in our understanding of how to decompose the system hierarchy and connect different pieces together. I know the concepts we just learned can be very abstract, so let us take the automobile assembly line as an example to see what these system attributes and concepts mean in practice. For the automobile assembly line, the purpose is to finalize the mass production process of cars. In order to do that, the function the system performs is to assemble different parts and components into a complete car. To describe the structure of this system, which should answer the question, what is the system like, we can say each sector consists of forklifts, robotic arms, conveyors, and the system behaves by forklifts transporting parts to the station, robotic arms installs it into a vehicle, and the conveyor supports transport the assembly into the next station. Once we draw the system boundary for our system of interest as the auto assembly line, we can identify the environment in which the system operates on and external systems which our system of interest contributes to and consumes from. This slide here shows some potential external systems which the auto assembly line will interface with. Similarly, with the auto assembly line as a system of interest, now we can look into the hierarchy of systems and identify different subsystems which form the auto assembly line. Here, these subsystems, such as the forklift, the robotic arm, could be considered as systems in their own regard. As we will see in later MBSE modules, MBSE provides flexible and abstract means for developing and representing the various models and parts and components of a system based on purpose, function, boundary, and interfaces. The concepts we have discussed here will provide a foundation for building the model-based representation of a system. Let us conclude this video by referring to the learning objectives which were shown early on. I expect that now you're able to define a system, distinguish an engineered system from a natural system, and describe the various attributes of an engineered system. Here we have discussed auto assembly line as an example of system of interest, and I would encourage you to think about a system of interest in your work environment and discuss its attributes on Brightspace discussion boards. Also, don't forget to check out the assignment tabs for this topic in Brightspace and complete the submission. Next time, we'll talk about systems thinking, which is a broader look for solving systems-related problems and challenges. Until then, enjoy MBSE.